welcome to Unit 1, Problem Solving and Critical Thinking. So in this first section, we're going to look at analyzing arguments. And what is an argument? Arguments use a set of premises. And premises just provide us information that leads to a conclusion, okay? And those premises support one or more conclusions. There's two types of arguments that we're going to look at. We're going to look at inductive and deductive. So what's the difference? For inductive reasoning, you're going to have fairly specific premises and those are going to lead to a conclusion. Okay, so some examples are like, if birds fly into the air but come down, people who jump in the air come down, rocks thrown in the air come down. The conclusion would be, well, what goes up must come down. Okay. With inductive arguments, we can try to find counter examples, and a counter example is a specific case that disproves a general statement or proposition. An example could be if I told you the product of two-digit numbers is a three-digit number. Okay, so you might look at two numbers that are two digits, like 37, and then multiply that by 25. So you've got two two-digit numbers multiplied together, give you a three-digit number. Now, is that always going to happen? Okay, so if I can disprove it, I've found a counterexample. And I can find a counterexample because if I was to multiply, let's say, 40 times 40, I would get a four-digit number, which is 1600. So that's my counterexample. Okay, the 1600 solution disproves that two two-digit numbers multiplied together will equal a three-digit number. You can see here that those two two-digit numbers equal a four-digit number. So with inductive reasoning, we've got fairly specific premises, right, which lead us to a conclusion. So now if we look at deductive reasoning, that's when you're given a general statement and from there, you should get a specific conclusion. So think of them as kind of, in reverse. Here you've got specific leading to general for inductive, and here you have general leading to specific for deductive. Okay, so an example could be if you had a statement like, all politicians are married, and let's say Senator Booker, who is a politician in New Jersey, right? He's a politician. So my premises are that all politicians are married and Senator Booker is a politician. So the conclusion you can draw from that is Senator Booker is married. So you've got your general statements and leading to a specific conclusion. All is general, right? So how exactly do we evaluate inductive arguments? So inductive arguments can't prove conclusions true, What we need to look at is the strength of the argument. Okay, so when we're looking at the strength of an argument, you're either going to have a strong argument or you're going to have a weak argument. Okay, what's the difference? Strong arguments make compelling cases for the conclusion. As opposed to a weak argument where the conclusion is not well supported by the premises. Okay, let's take a look at a couple examples. So what I would like you to do is pause the video and read through the problems, and you can try these on your own and then unpause it when you're ready and we can review them. The 10 symbols that we use to write numbers, namely 0 through 9, are called digits. In each example shown below, the sum of two two-digit numbers is a three-digit number. Is the sum of two two-digit numbers always a three-digit number? Find a counterexample to show that the statement, the sum of two two-digit numbers is a three-digit number, is always false. So in the example we did earlier, we looked at the product of two two-digit numbers. Here we're looking at the sum. Sum means to add. So here's two two-digit numbers, two sets of them, where we're adding them and we're getting a three-digit answer. So is that always going to be the case? So can you think of, two two-digit numbers that you add together that it would give you not a three-digit number? And there's a lot of different answers you could come up with, but if I just change the first example there, 47 plus 73, if I change it to, let's say, 32, you got 9 and 7, which is a two-digit number. So you just disproved it. That's your counterexample. In the next set, we're going to look at the list of numbers and see if we can find a pattern. And then we're going to use the pattern to find the next number. Okay. So in this first example, we can see that the numbers are increasing slowly, right? If they're increasing rapidly, then we would say that we must be multiplying maybe to get from one number to the next number. But since it's increasing slowly, let's try addition. So are we adding a number to get to each number? So if I take the second number and subtract the first number, 12 minus 3, I get 9. So that means I had to add 9 to 3. Now, is that always going to work? Do I add 9 to 12 to get 21? Yep, because 21 minus 9 is 12. 30 minus 9 is 21. 39 minus 30 is 9. So I'm adding 9 to each of these terms. So the next term would just be 39 plus 9, which is 48. Now on that next problem, in number 2, we can see the numbers are increasing much more rapidly. So here we're not adding a specific term, right? Like if I take 12 minus 3, that gives me 9, but 48 minus 12 is not 9. So I know I'm not adding 9 to get to each term. So let's try multiplying and dividing. 12 divided by 3 gives me 4, so that means 3 times 4 is 12, right? Does that work if I multiply each of these numbers by 4? Will it give me the next number? And it does. 12 times 4 is 48. 48 times 4 is 192, and so on. So I need to do 768 times 4, and if I multiply that, I get 3072. In number 3, you have your, again, numbers are increasing, but at a slower rate. Okay, this time, if I do 4 minus 3, I get 1, but 6 minus 4 is not 1, it's 2. Okay, so there must be some other pattern going on, maybe. So let's see what it would be. So if I add 1, 3 plus 1, it gives me 4. 4 plus 2 gives me 6. 6 plus 3 gives us 9. 9 plus 4 gives us 13. 13 plus 5 gives us 18. And what do you think we would do to get the next number? Well, you can see here that the pattern increases by 1, starting with the number 1. So the next term would be 18 plus 6, which is 24. And then in the last one, number 4, again, it's increasing at a more rapid rate. So here, if we divide 6 by 3, we get 2. 18 divided by 6 is 3. So we're not increasing at the same rate. Here, it looks like it's going to be times 2, times 3. And then now it's back to times 2. And then 36 times 3 is 108. 108 doubled is 216. So now I need to multiply 216 by 3 to get that last term, which would give me 648. In letter C, a movie director tells her producer not to worry, her film will be a hit. As evidence, she cites the following facts. She's hired big stars for the lead roles, she has a great advertising campaign planned, and it's a sequel to her last hit movie. Is this an inductive or deductive argument? And we need to evaluate its strength. Okay, so what do you think, inductive or deductive, and why? If you said inductive, you're correct. There's 3 specific pieces of evidence there, right? So what's my evidence? My evidence is she's hired a big star or stars for the lead roles. That's one piece of evidence. So that's a premise. She has a great advertising campaign plan. That's a second premise. And it's a sequel to her last hit movie. So you've got 3 premises, and then what's the conclusion? That the film will be a hit. Okay, so you're going from specific premises to a conclusion, which is that the movie is a hit. And, is this a strong argument? What do you think? If you said weak argument, you're correct. And that's because, we all know that you can have movies that are planned out really well and they can be a flop, right? So it does not necessarily mean, because of those 3 statements, that the movie is going to be a hit. So this is inductive reasoning, and it's a weak argument. And what I'd like you to do on your own, and I'm not going to answer the question, but you can think about it, is suppose you're the director in that example, and the producer says she needs more evidence that your movie will be a hit. How might you gather additional evidence to strengthen the case for your movie? Let's look at check your understanding number 2. And again, please feel free to pause the video and then unpause when you're ready. So in this problem, we need to evaluate the argument and discuss the truth of its conclusion. The argument is, geological evidence shows that for thousands of years, the San Andreas Fault has suffered a major earthquake at least once every 100 years. Therefore, we should expect another earthquake on the fault during the next 100 years. So what do you think about that? First of all, what type of argument is it? Inductive or deductive? Okay, it is inductive. And this is because it cites many specific past events. Okay, and what do you think about the truth of its conclusion? So if someone was saying this to you, would you be able to infer that another earthquake will occur just because, there was a major earthquake at least once every 100 years, and because it's been over 100 years, in this case, it's, I don't know the exact, but I know it's over 100, that we should be due for a major earthquake there at any moment. That's not necessarily the case, right? So the argument doesn't really prove another earthquake will occur. It suggests maybe a strong likelihood because of the pattern that's been held for thousands of years, but it does not prove that another earthquake will occur. So it's kind of a weak argument, right? And the conclusion just suggests a strong likelihood. Okay. Let's look a little bit more at deductive arguments. So how do we evaluate deductive arguments? Basically, we're going to look at two criteria. Okay. The first is the argument is valid if the conclusion follows from its premises. Okay, so, regardless of the truth, by the way, okay, that's something different. And then it's going to be sound, so a sound argument, if it's valid and if its premises are all true. Okay, so we have some tests to determine whether deductive arguments are valid. One of those things we're going to look at is a Venn diagram. So we'll see quite a few of those. Okay, they're a great visual way of proving if the argument's valid. Okay, we need to ask ourselves, does the diagram contain all the information contained in its premises? And then we also need to check to see whether the Venn diagram confirms the conclusion. If it does, it means it's valid. Otherwise, it'll be invalid. Okay, let's take a look at an example. So this example, we're going to evaluate the validity and the soundness of the following argument. Okay, remember, validity does not mean that it's truthful. Okay, that's something different. Just that the conclusion follows from its premises. And a sound argument needs to be valid and the premises are all true. Okay, so here's our two set of premises. All fish live in water, which is a very general statement, right? Whales are not fish. And the conclusion I can draw from that is, well, if all fish live in water and whales are not fish, then whales do not live in water. Okay. So what is the validity of this argument? Okay. Well, we know that the first statement is true. And we know that the second statement is also true. Whales are not fish, right? They're mammals. And we know that whales do not live in the water is false. They do live in the water. Okay? So how do I determine if this is valid or not? We're going to draw a Venn diagram. So to do that, I'm going to first draw a rectangle, and I'm going to place a larger circle if I can get it to make this correctly. There we go. Okay. And then I'm going to have a smaller circle inside. All right, now what is the purpose? Well, think of the smaller circle as the subset of the larger circle, okay? So what would be the larger circle here? Well, we're talking about, things living in the water, right? And we know that fish aren't the only things that live in the water. There's other things. So for the larger circle, we're just going to pretend that's going to be things that live in the water. And fish are a subset of that, right? Because we know fish do live in water. Okay, so you can see here that all fish live in the water. Okay, so that represents my first premise there. Whales are not fish. Okay, well, they're not fish, right? And it also says whales do not live in the water. All right. So we know whales do live in the water, though, right? So the conclusion, it should be on the outside of this because they're not fish, right? And we do know that things that live in the water do include whales, but the conclusion is saying they don't live in the water. So we're going to put a little X right there, okay? Again, which just signifies like we know that whales do live in the water. So the conclusion needs to be outside things that live in the water, okay? But it isn't because we know that whales do live in the water, right? So whales are not fish, so they can't be inside here. But we know they live in the water, okay? But the conclusion says they don't. So therefore, this has to be an invalid argument. Let's look at another one. And we know that if it's invalid, it can't be sound, right? Because a sound argument has to have it has to be a valid argument, and then the premises have to be true. So it's not even valid, so it can't be sound. Okay, you can try the next one on your own. If you don't feel comfortable yet, you can keep the video rolling, and we can do this one together. So again, same thing. We're evaluating the validity and the soundness of the argument. So the first premise says that all 20th century US presidents were men. And the second premise says John Kennedy was a man. So what conclusion can you draw from that? That John Kennedy was a 20th century US president. Okay, so let's draw a picture first. All right, I got my larger circle in here, which is going to represent the larger set. And then I have my smaller circle inside, which is going to represent my subset, okay? All right, so that first statement says all 20th century US presidents were men, okay? So that means that's going to be my larger set, all men, right? And we know that all of the 20th century US presidents were men. So that's going to be my subset. Okay. So our conclusion says John Kennedy was a 20th century US president. Well, where would I put my X for my conclusion? The conclusion requires the X to be inside the president circle, right? But it isn't. And the argument would be invalid. Sorry, my pen is acting up there. Okay. So again, when the reason I'm putting the X there is because it says John Kennedy was a 20th century US president, right? And John Kennedy was a man, right? So that's true. And the first premise was true. All 20th century US presidents were men. Okay, but in order for the conclusion to be true, the X would need to be inside the president's circle, but it's not. So the argument is invalid. Okay. Let's take a look at some conditional deductive arguments. So here you have four basic conditional arguments. You've got what's called affirming the hypothesis, and then this is the basic structure that it takes on, okay? If P, then Q. If P is true, Q is true. So then you have a valid argument. Okay, the other valid argument is called denying the conclusion. If P, then Q. So if Q is not true, P is not true. Okay, and the reason is because in order for a Q to happen, P has to happen first, right? Like if you do this, then this will happen. And Q is not true, so therefore P is not true. That's another valid argument. The two in the middle are invalid arguments. So you look at the structure. If P, then Q. Q is true, P is true. Okay, so notice how it's different. In affirming the hypothesis, first we know P is true, so therefore Q is true. Okay, in this structure, affirming the conclusion, Q has to be true first, and then P is true. Well, that is not necessarily the case. Okay, so I'll give you an example. If I said something like, if I go snorkeling, then I go to the Bahamas, right? So I went snorkeling is true, and then I go to the Bahamas. So that would be valid because I did go snorkeling, and in order for you to go to the Bahamas, you have to go snorkeling first. Okay, so why would this be an invalid argument? So same statement, if I go snorkeling, then I go to the Bahamas. I went to the Bahamas. Well, just because you went to the Bahamas doesn't mean that you went snorkeling. You could do a lot of things in the Bahamas, right? So that's invalid. And then the other invalid argument is called denying the hypothesis. And that says, if P, then Q. If P is not true, Q is not true. Well, that can't be because in order for Q to happen, P has to happen. Okay. Let's look at an example. So we're going to use a Venn diagram to show that the argument concerning Carlos and Chicago below is valid. Okay. The premise says, if a person lives in Chicago, then the person likes windy days. Second premise says Carlos lives in Chicago. So what can you conclude from that? Carlos likes windy days. Now, without even making a Venn diagram, if you look at the different conditional arguments and look at their structure, right? If I call this first part here P, so a person lives in Chicago, and then I call the second part Q, the person likes windy days, okay? If you relate it here to this, it's if P, then Q. P is true. Carlos does live in Chicago. So Q, Carlos likes windy days. That's true. That's a valid argument, and it's valid because of affirming the hypothesis. All right, now, what would that look like if you were to make a Venn diagram? So let's make a Venn diagram. Here's my general statement, my larger set, and then I've got my smaller subset here. All right, so my larger set, right, is it would be likes windy days, because we know that if a person lives in Chicago, then they like windy days. So the windy days is going to be your larger set. And then the person living in Chicago would be your subset. Okay, and it says Carlos lives in Chicago. So my X is going to go in here, and it also shows me that Carlos likes windy days, which is what the conclusion is. So that's a illustrated way of showing that the argument is valid. Okay, so, and the reason is because the X is inside the likes windy days circle, which is what your conclusion is. Okay, and I'll put here too, the reason we know that is, again, it's the affirming the hypothesis. Okay, please pause the video and try these on your own, and then you can unpause when you're ready, and we can go over this. And there are 3 problems to look at there. Okay, so again, you're using the Venn diagram to test the validity of the argument, which affirms the conclusion. If an employee is regularly late, then the employee will be fired. Drew was fired. Drew was regularly late. Okay, so if I, again, take a look at my P and my Q. Okay, so what would P be here? P is going to be the first part after the if. So an employee is regularly late would be P. Okay. And then you've got Q, which is the employee will be fired. So here, if P then Q, right? Q happened, then P happened. So if you go back and look at the structure, again, that's referring to this structure, which is affirming the conclusion. It's an invalid argument to make. Okay, let's see why. So if I make a Venn diagram, think about like what your larger set is going to be, and then what your smaller, your subset going to be. Let's try that again. Okay, so if an employee is regularly late, then the employee will be fired. So we know that anyone that's late is going to be fired, right? Okay, so here, Drew was fired, right? But it says Drew was regularly late. So we don't know if Drew was regularly late, right? All we know is that he was fired. He could have been fired for various other reasons. So my X would go like on the outskirts there. Okay, because again, we can't put it inside, because even though Drew was regularly late, that doesn't mean that Drew was fired, right? We don't know if he was regularly late or not. So that's going to be invalid. And it's invalid because we're affirming the conclusion. Okay. If you liked the book, then you loved the movie. You did not like the book, so therefore you did not love the movie. Okay, so let's again take a look here at the structure. before we make our Venn diagram. Okay, so here's P, you like the book, and then here's not P, so you did not like the book, right? So this is what we call the negation of P. And then here you have you loved the movie, and then here's the negation of that. You did not love the movie. So in other words, it's like saying, okay, here's P and Q, not P, not Q. So if you go back and look at the structure again, we're looking at denying the hypothesis. Because P is not true, and then Q is not true. Okay, but let's look at a Venn diagram. Think about what your more general set is going to be, and then we'll look at the smaller subset. All right, so our general set, right, has to do with loving the movie. And if you liked the book, then you love the movie. So we're going to put the book people in here. They're going to go inside the movie. Because if you liked the book, then you liked the movie, right? Or you loved the movie. Okay. You did not like the book. So I can't put the X in here because you didn't like the book. You also did not like the movie. You did not love the movie. So the X needs to go out here. So since it's placed on the border, the reason is because the premise does not tell us whether you loved the movie. So this is an invalid argument. And the reason it's valid is denying the hypothesis. In my next problem, a narcotic is habit forming. Aspirin is not habit forming. So my conclusion is aspirin is not a narcotic. Okay, so let's draw a Venn diagram for this. Let's try that again. Okay. So we've got narcotics being habit forming, right? And it says aspirin's not habit forming. So we've got habit forming here. And we know that our narcotics are habit forming. Now it says aspirin is not habit forming. So if it's not habit forming, then that means it also is not a narcotic, right? Because narcotics are habit forming. So my X is going to go out there. Okay? And the reason is because aspirin is neither a narcotic nor habit forming. So because the X is outside, right? Look at your conclusion, aspirin is not a narcotic. So because it's outside, that's a valid argument. And if you look again at like the P's and Q's, you can relate it back to denying the conclusion, right? So if P, then Q, Q is not true, P is not true, right? So here, Q is not true. Aspirin is not habit forming. So therefore, P is not true. Aspirin is not a narcotic. So that would be the denying the conclusion. So deductive arguments have a chain of conditionals. Let's look at when we have three different statements here. So you've got your two premises and then your conclusion, but there's three statements. There's P, Q, and R. So the first premise says if P, then Q, and the second premise says if Q, then R. My conclusion is if P, then R. So This is referred to, it's a valid argument, but it's also known as, in logic, it's called the law of syllogism. And we'll cover logic at the end of this course. But I always relate this to a family tree. So if you want to think of it as like, think of you as P, so me. If I'm related to Q, which is, let's say, my mom, and Q is related to R, which, let's say, your mom is related to your grandma, right? Then what's the conclusion you can draw? That you are related to your grandma, right? So that is your law of syllogism, which is a valid argument there. Okay. So here we wanted to determine the validity of the argument. If elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. So, is this a valid argument? All right. Let's look at it as the different premises, right? So, in the first premise, I'm told that if Maria Lopez, or if elected to the school board, Maria Lopez will force the school district to raise academic standards, right? So that's my first premise. So premise one is something like, if Maria Lopez is elected, then what will happen? The school district will raise academic standards. Okay. Premise two from that statement, which will benefit my children's education. So, what will, if the school district raises the academic standards, right? So, if school district raises the academic standards, right, what will happen? The children will benefit. And then what would be the conclusion? Therefore, so that's where my conclusion is, the children will benefit if Maria Lopez is elected. So if Maria Lopez is elected, my children will benefit. Okay, so here, if you break it down like that, you can say, like, here's P. So if P, then Q. If Q, then R. And then what? If P, then R. So that's a valid argument. And again, it's in logic, it's called the law of syllogism. Okay, you can pause the video and try this problem on your own, and then unpause when you're ready. Okay, you have to determine the validity of the argument. We agreed that if you shop, I make dinner. We also agreed that if you take out the trash, I make dinner. Therefore, if you shop, you should take out the trash. So here, this is an invalid argument. Okay, if you think of it like this, you've got three statements. We'll call them P, Q, and R. One of them, the first one is, we agreed that if you shop. So just think of P as like you shop. Q is that you make dinner. Okay, and then what's the third thing that's going on there? The third statement is that you will take out the trash. Okay, so recall that it should go something like, if P, then Q, if Q, then R, therefore, if P, then R, if that's a valid logical argument. Okay, so here, P is you shop, right? So everywhere it says you shop, I'm going to highlight it orange. And then you've got Q, which is you make dinner. So everywhere it says something about making dinner, I'm going to highlight that. Okay, now look at that for a second, right? The Q should be at the end, which is where the blue is. So right there you can see it's not matching up. Okay, so therefore, this is an invalid argument, okay, because it should be blue over there, and it's not. It's not taking the same form. There's no chain from P to R, in other words. So invalid. Okay, so to tie everything together, let's kind of put this all together, induction and deduction in math. So as you can see, a lot of math requires proof, right? Deductive arguments demonstrate a claim, right, or a theorem. Induction helps in discovering patterns or conjectures, and then deduction is used to prove these conjectures. So let's write a couple of that stuff down. That's important. Math relies on proof. Okay, we love proof. What is proof? Proof is a deductive argument that demonstrates a claim. Okay, and you've got induction. And induction helps in discovering patterns and conjectures. Okay, and then you have deduction, which is used to prove the conjectures. Okay, here's an example. We're going to test this rule. It says for all numbers A and B, so they could be anything, A times B equals B times A. Okay, so let's pick two numbers. Like let's say, does 6 times 7 equal 7 times 6? Well, I know 6 times 7 is 42, and 7 times 6 is also 42. So in other words, it doesn't matter if we rearrange the terms in the expression, we still get the same answer, right, for multiplication. And you can try that with anything. So that's a strong inductive argument in favor of a rule. Okay, we still haven't proved the rule, but it gives us confidence. Okay, so I'm going to put a little disclaimer here that we still haven't proved the rule. So keep that in mind, okay? It's just a strong argument because you can pick any two numbers and multiply them together in any order and still get the right answer. Okay. And then to wrap everything up, you can try the last one on your own and then unpause it when you're ready to go over it. Suppose you cannot recall whether adding the same amount to both the numerator and the denominator, remember the numerator is the top of the fraction and then the denominator is the bottom of the fraction, such as 2/3 is legitimate. So in other words, you're wondering whether it's true that for all numbers A, 2 over 3 equals 2 plus A over 3 plus A. Okay, so if A equals 0, right, then is that a true statement? Yeah, because 2 plus 0 is 2, and 3 plus 0 is 3, and 2/3 equals 2/3, so that's true. But what if I change A to 1? Does it still work? 2 plus 1 over 3 plus 1, does that equal 2/3? Well, 2 plus 1 is 3, and 3 plus 1 is 4, and I can't reduce 3/4, and it most certainly doesn't equal 2/3. So therefore, It's not true that for all numbers a, 2 over 3 equals 2 plus a over 3 plus a. So that's a no. And that concludes this lesson on inductive and deductive reasoning. If you have any questions, please reach out to me. I hope you all have a great rest of your day.